Welcome. In this video, we're going to go over a classic pumping problem that you'll see a lot in calculus courses or physics courses. And those of you in my online course should have already looked at the Canvas page and have a key of the notation required right above on your written notes. So how are we going to figure out work in this case? Well, remember, work for pumping problems is rho times g, and I'll go over those in a second, times the integral from a to b of dy, or d of y, times a of y, and then little dy. So what are all these symbols, these variables I'm using? Well, this is the density of the liquid. G is the acceleration due to gravity. This function, big D of y, is the distance liquid travels. This a of y here, this function, is the area of a slice of water. And then this is our lower water level, and this is our upper water level. Okay, so now that we have all that notation down, let's kind of read through this problem and see if we can't translate this information to this sketch. Suppose we have a 12-meter tall cylindrical tank with a base radius of 6 meters, and it is completely full of water. Okay, so let's hang on right there and just start sketching an axis. And you can kind of choose wherever you want to sketch it. And frankly, a lot of books just do really weird things where they have you turn it awkwardly to supposedly make it easier, but I really have found that tricky. So I'm just going to keep my x-axis here. And then the y-axis is going to be right down the middle here. And we know that this tank is 12 meters tall. So this value here at the top, this is 12 meters. Furthermore, we know that the radius is 6 meters. That means this distance here is 6 meters, but this distance also is 6 meters. And this distance, oops, that's too far. This distance here is also 6 meters. So I'll go ahead and mark that with 6. Okay, now we've translated some of this problem onto the sketch, so let's keep going. So we're going to suppose further that the outflow pipe is located at the top of the tank. So that's here. It's just here. We're not even going to change that. That would change how far the water travels. But for now, we're pretending it's right at the top so we don't have to take anything extra into account. So how much work is required to pump the water over the top edge of the tank? What if the water was pumped to an outflow pipe located 15 meters from the bottom of the tank? So here we'll have an alternative version that we'll get to, but first let's answer this question. How much work is this going to require? So this is our question 1. Well, let's start putting this together. And I'll go ahead and write those here on the side. Rho we're taking to be 1,000 kilograms per meters cubed. And so gravity, G, is 9.8 meters per second, so second squared. So these two are just constants multiplied out in the front. 1,000 times 9.8 is just 9,800. So this becomes 9,800 times the integral. And remember, A is the lower water level, and A here, this would be A, that's at y equals 0. So we're going to go ahead and write 0 here. B is the upper water level, which is here at y equals 12. Now let's figure out what D of y is. And so I'm going to ask you to write a little table, and I won't do this again, but for this first introductory problem, it's probably a good idea to figure out D of y by finding a pattern. So let's say, well, here's y, and this is D, the distance. If y equals 0, so we're here, how far does the water here have to travel? All the way to overflow from the outflow at the top. Here's the outflow where the water is going to pour out. Well, that's going to have to travel vertically 12 meters. What if we're located here at 1 meter? Well, this water is already 1 meter above. That's this distance. So this is going to have to travel all the way up 11 meters. Okay, let's try this again for 2 meters. So say this is 1, this is 2 meters. The water here is going to travel how far vertically? If you said 10 meters, you're correct. Now, without computing anything, we can see that water that is, say, located at the 3-meter mark here, well, that's going to have to travel a distance of 9 meters. And you can keep going to fill in this table, but I'm going to stop here. And I'm going to ask you to think, well, how did we work all these out? Well, this is just 12 minus 1. This one here is 12 minus 0, 12 minus 2, 12 minus 3. So really all we're doing is taking this height and subtracting the location, the vertical location of that water slice. So if water is located at, say, y meters above, so somewhere, anywhere, just at some y value, we know the distance it's going to travel is 12 minus y. So that would go here. Okay, so now let's figure out the area of a slice, and that's a of y. So for that, let's go ahead and sketch a picture. So let's pretend this water is like solid, like cheese. And you can just slice through this. So here is a slice of water. Well, what would this slice look like? Say we actually could cut this with a knife and remove it. When we did that, this slice would look like this. Does that look familiar? It's a circle, it should. So circle, we want to find the area of the circle. Well, for that, we need the radius, which is here. And we know what that radius is. This distance is 6, so this has to be 6. So the area in this case is equal to pi times 6 squared, or just 36 pi. And I'm going to point out that in this case, it's constant. It's not going to change. The area of each slice is going to be the same, so we actually won't have a function of y. We just have this constant function. So a of y is 36 pi. For other shapes of tank, say a cone, we are going to have some change in the radius as we move upward. So in those cases, we would have y's in our a of y. But in this case, we just have 36 pi. So let's go ahead and multiply this by 36 pi. So clearly, as you can see, the integration is easy. It's this setup that can be a bit of a problem. So I can rewrite this entire integral now by pulling out all the constants. This is a constant out to the front. 9,800 times 36 is 352,800. And that's pi. And we're integrating from 0 to 12, this distance function, 12 minus y dy. So this is 352,800 pi times 12y minus y squared over 2 from 0 to 12. So pause your video right now and see if you can figure out what number should go here when you evaluate this expression for these endpoints. So you should have gotten 72. This tells us that it takes this much work. So this is 25,401,600 pi joules. If you want to write this out as a decimal, we need to use scientific notation for that. So let's multiply this out first. So this is 79,801,480 joules, which is just about 7.98 times 10 to the 7th joules. So hopefully you can see that these problems aren't too tricky. They're really just a setup. So let's tackle this second problem here. So what if the water was pumped to an outflow pipe located 15 meters from the bottom of the tank? So here's question 2. We've already answered question 1, so we're done with this one. And for question 2, I'm not going to work out the number. I'm just going to show you the setup. Well, if the outflow pipe is located, say, 15 meters, and I'm running out of space, I'm just going to say that 15 is right up here. So if it's located 15 meters up, and this is where the water comes out of, this pump here, well, that means that when the water travels vertically, it has to travel further up. It has to travel a vertical distance of 15 meters rather than 12. So the only change really would be this value here. So our integral now, the work would be 36 pi times 9800 times the integral from 0 to 12 of 15 minus y dy. And you may be wondering, well, I didn't change this 12 here. And no, I didn't, because the upper water level is still located at 12. The water doesn't just magically rise up 3 meters if we move the outflow tank and start at that position. Now, I suggest you work this out independently. It isn't too tough to integrate this. I hope this video has been helpful.